In a previous video, we saw that not all Newtonian systems allow for a Lagrangian and a Hamiltonian. And if you ask me what systems are these, I would tell you that they are the non-conservative ones, the open ones, the ones that do not conserve entropy. And some of you would say, wait a minute, I have seen a Lagrangian or a Hamiltonian for a dissipative system. It was a time-varying Hamiltonian. But how can it be? You see, Hamiltonian systems have to conserve volumes of phase space, and around an equilibrium, the volume must shrink. So are these Lagrangian and Hamiltonian really describing dissipative systems? No, they're not. But you should not take my word for it. You should go through the details yourself. So we will go through one example, a particle under linear drag, and we will find a Lagrangian and a Hamiltonian for it, and we'll see that they're not quite right. And I'll argue that they're actually describing something else, but you'll be the judge and see what makes most sense to you. Finally, I will conclude with a small rant about physical precision versus mathematical precision. So if you want to see me ranting, stick to the end. First of all, I want to make a distinction between two things, the kinematics and the dynamics. The kinematics describe the motion of a system in space-time. So kinematic variables are position, velocity, and acceleration. And this is what Galileo studied by letting things go on an inclined plane, see how they behaved and so on. So you just have a description of what is happening. And then there is the dynamics, and the dynamics describes the cause of motion. So forces, mass, momentum, and energy, all these are dynamical quantity in that sense. It tells you why things do the things that they do. And this is what Newton did with his first law. So we want to make sure that whenever we are having a description of the system, we're matching both the kinematics, what we see, and also the cause of motion, because mechanics is the description of both of these things, not just one. And since we're going to be talking about the different formulations of classical mechanics, we should remind us what they are. You have Newtonian mechanics, and the state is given by position and velocity. The dynamics is imposed by a force, which is a function of position, velocity, and time. And you have a law of evolution that it's F equal ma. More generally, is the derivative of the kinetic momentum. In Lagrangian mechanics, the state is described by position and velocity as well. The dynamics is given by a Lagrangian, which is a function of position, velocity, and time, and the evolution is given by the Euler-Lagrange equations. In Hamiltonian mechanics, instead, the state is given by position and conjugate momentum is a dynamic quantity, so the state of the Hamiltonian system already is both a kinematic and dynamic quantities. And the dynamics is given by a Hamiltonian, which is a function of position, conjugate momentum, and time. And the evolution is given by Hamilton's equation. So as we said before, we want to talk about a dissipative system, and we take the simplest one, possibly the particle under linear drag. You have something, and you have air resistance, and in some condition, to some approximation, the air resistance is proportional to the velocity. And so we have F equals ma, the first law, and the force is equal minus bv, because the force is going to be in opposite of the direction of motion, opposite of the velocity. Okay, we want to solve this system. Well, the acceleration is just the derivative of velocity with respect to time. We take the mass on the other side. We have a linear equation. The solution of this is an exponential. V0 is going to be the initial velocity, and then everything will decay with a factor of b over m. We can plot this. This is going to be the velocity, and this is our exponential. We can integrate the velocity and have an initial position, and this is going to be the graph of the position, which will tend to the equilibrium of x0 plus m over b v0. And if we derive the velocity, we get the acceleration, which will start negative, opposite of the velocity, and will go to 0 at equilibrium. So there you go. This is the kinematics of the system. If you're seeing this system, this should be nothing new. And now let's look at the dynamics, meaning the energy and the momentum. The energy is going to be just 1/2 mv squared, and we saw the graph for v. We had the expression for v. This is going to be v0 squared, and then the exponential, we have a factor of 2 here, which is the same factor of 2. So the exponential will go down, let's say, faster than the velocity does. And the momentum is just equal to conjugate momentum, so P equals mv, and so you basically have the same graph for the velocity, except that you start at mv0 instead of v0. Okay? So this is all hopefully very straightforward, and now we want to say, can we find a Lagrangian for the system? A Lagrangian that matches the equation and the solution. And look at this, let's try with this Lagrangian. L equals 1/2 mv squared e to the b over mt. We apply our Lagrange equation. We have the derivative of L with respect to x. There is no dependencies of x, and this is 0. And this has to be equal with the derivative in time, the derivative in velocity of L. And so we put L here, and we do the derivative of velocity. Well, this is the only term that depends on the velocity, so this 2 goes down. We have mv e to the b over mt. And now we do the derivative in time. Here we have two actual things that depend on time. We have the velocity and we have this exponential. So we do a product rule. We first derive the velocity, we get an acceleration, and then we derive this term, we just get a b over m factor in front. We can collect now the term e to the bm t, and we just have m plus bv here. This has to be equal to 0, and so this part has to be equal to 0, so we have ma equals minus bv. And this is exactly the equation for a particle under linear drag. So we do have a Lagrangian. We do have a Lagrangian that gives us the equation of a particle under linear drag. And can we do the same thing for a Hamiltonian? Well, we have the Lagrangian. We can find the momentum by taking the derivative of the Lagrangian with respect to velocity, and then we can calculate the Hamiltonian as the product of momentum and velocity minus the Lagrangian. So let's do it. P is the derivative of L with respect to V, and again, we did it before, there is just the 2 that goes there, so it's mve to the b over mt. Therefore, we can now reverse invert this relationship, and so v equals p over m e to the minus b over mt. And now we have Hamiltonian is equal pv minus L, so we take v and we substitute it here. We have L, which is this, we put it here, and we substitute v that is here. We do some calculation, and if you want, you can pause to digest this a little bit better. But what you basically get is you're gonna get a p squared over m here, a minus 1/2 p squared over m here, with the same term here for the exponential. So your Hamiltonian is just 1/2 p squared over m e to the minus b over mt. Okay, so we seem to have a Hamiltonian for a linear drag, and we have a Hamiltonian for a dissipative system. So what I was talking about there, that we can't do it. And let's actually apply the laws of motion and see what we get for Hamiltonian mechanics. This is the Hamiltonian. The derivative of the momentum in time is the derivative of Hamiltonian with respect to position. There is no position dependence, so the momentum stays still. And then we have the derivative of the Hamiltonian in position to get the velocity. And so again, we are just deriving with respect to momentum. So the 2 goes down. We have p over m e to the minus b over mt, which is exactly what we had before. The velocity is an exponential that starts at essentially velocity and goes down. And we can integrate now the position, and we get the same solution that we had. We get the same kinematics. So it seems to all be working fine, right? The issue is that there is a mismatch in the dynamics. I mean, if you saw before here the momentum is constant. And this should be a puzzle. And so the momentum is constant while mv, the kinetic momentum, goes down like an exponential. And if you look at the Hamiltonian should be the energy, and the energy does go down, but it doesn't go down as fast as the actual energy does. So there is a mismatch in the dynamics. And this is where some people are saying, well, it's because the Hamiltonian is not always the energy and the conjugate momentum is not always the kinetic momentum. And that might be, but then what exactly are they? You can't just say, oh, they're not the same without telling me exactly what they are. Otherwise, like, what are we talking about? And the issue here is that this is actually kind of true, because the momentum and the conjugate momentum and the kinetic momentum have really this expression that the conjugate momentum is the kinetic momentum plus essentially the vector potential for the M field or the other field that you might have. And so it is true that the kinetic momentum is not always the kinetic momentum. It's also only true when you are essentially, when you do not have forces and you are in an inertial frame. That's essentially the only case where it's true. But it has nothing to do with what we saw before. This is not dependence that we saw in this Hamiltonian Lagrangian for a linear drag. And the issue that you have here, it's something that looks more like this, that you have no drag, right? You imagine that you have a particle coming in a region where there is no drag, and there you have that P equals mv. And then you do have drag, and so at the beginning here, you're going to have the P equals mv, but then as you go down, right, P remains constant and mv is decreasing. And then let's say that you go to another region where you have no drag. And in principle, you still have P equals mv. So what happens there? Like the conjugate momentum drops suddenly? Like it's not a clear picture what's happening. And these type of things do not happen with this relationship. So something really sketchy is going here. And let's see if maybe there is a better way to resolve this issue. So we saw that conjugate momentum is constant, and the velocity goes down like an exponential. And suppose we really have that P equals mv, because we do not have potential forces and so on. So this relationship should hold. And so the mass, we just define it to be the P divided by V. And so you just get that the mass is equal m e to the b over mt. That is, you have a system with variable mass. So that m is really just a constant, it's not really the mass, it's just the initial mass, and then mass is going to change. Okay, how would that look like? Can we actually give a physical system that actually matches these conditions? And yes, imagine that you have a system that is going, and while it's going, it's sort of attracting mass from all other direction, and the mass sticks to the system in a way that it's absolutely symmetric, such that the momentum does not change. It's just getting exactly momentum contribution from all parts, and so the momentum does not change, but the mass increases. And of course, if the mass increases and the momentum does not change, then velocity must increase and the system must slow down. And since this increase in mass is exponential, at some point the mass is essentially going to stop. And so this is a very different system than a particle under linear drag. And would that system work would it give us the same equation? Well, we have to verify that. And we have to use in Newtonian mechanics the rules for a variable mass system. This is a variable mass system where there is no change in momentum. So it's just, you're gonna just have that the force is equal to the derivative of the kinetic momentum. And this time the mass is time varying. So when you do the derivative, you're gonna have the two terms for the product rule. And we can just substitute m hat because we know the increase in mass. And so on one side we have m hat a, which is m a multiplied by m e to the b over mt. The force is going to be 0 because there is no net force acting on the system, and this term here is going to be the derivative in time of the mass. And again, the way that the derivative of time this works, you just take this factor and stick it in front, and so this term is going to be minus bv e to the b over mt. And this is kind of similar to what was happening before. Now we have these two factors that simplify, and so we're going to have ma equals m minus bv. But this ma is not really the force that this m is a constant, it's not the mass. And this is sort of an apparent force that we have because the mass of the system is increasing. And so we have the same equation as a particle under linear drag, but with different physics. And this is sort of the first point, is that you can have the same equations, but the system is different. So the equations by themselves are not enough to tell you what systems you have. Okay, so how does it work then, the Hamiltonian for a variable mass system? Well, it works in the same way. We have our m hat that is equal to this factor, and we have the momentum, conjugate momentum, velocity, the Hamiltonian and Lagrangian for as we had them before. But now what happened, remember, this is what we had before. This was the Hamiltonian that we had before. We can take this term and put it underneath, and we're going to have this term. And so we just have p squared over m hat, which is going to be equal to 1/2 m hat v squared. And this is exactly the energy. And so the Hamiltonian now is the energy. And so the dynamics of the system is now correct. And so we don't have the system with a different dynamics like we had before. We have a Newtonian system, and therefore a Lagrangian system, that match the dynamics, where the energy is the energy and the momentum is the momentum. So we could say that the Hamiltonian and Lagrangian that we had before are not really describing a particle under linear drag because the dynamics does not match, but they can be used to describe a particle that has a variable mass in the same exact way that we saw before, because they not only match the kinematics, but also match the dynamics. And so again, this is the issue. The same kinematics, the motion of the body, can be achieved with different dynamics, the causes of motion. You can see something and looks the same as something else, but the causes of motion are different. And the Lagrangian and Hamiltonian and any mechanics have to tell you a particular cause of motion. And here's the thing, the Lagrangian and Hamiltonian gives you a particular dynamics dynamics for each kinematic. So they give you the momentum, the energy, and so on. So how does the Lagrangian and the Hamiltonian pick the dynamics? Is there a rule that we can pick? We saw that there was a variable mass system, but can we have something, for example, where the mass is not varying, so that we can compare apples to apples? Mass with the fixed mass with our system with a fixed mass. And so let's compare the motion of the free particle and the motion that we had under this potential equations. The free particle is x0 plus v0 t, and this damped motion is x0 plus v0 plus some other term that depends on that t, that we call t hat. Okay, so these two things look very similar, and quite frankly, they are, there is just one variable transformation away. We could put that t is equal m over b, 1 minus e to the b over m t hat. That means we basically can say, look, this is actually this system seen with a different clock. We have a non-inertial clock, a clock that it's slowing down or going faster, right? The unit, the second of unit, the unit of a second for this clock is changing as time goes on. And you could say, oh, this is a very weird thing to do. But these are exactly the same thing that we do in relativity. In relativity, we go to generalized coordinate and we basically say, look, we don't care what type of clocks you have, you don't care about what rods you have, you can have everything nonlinear. And these are the type of transformation that we allow in relativity. So let's try allowing this and see what happens. All right, so we actually, at this point, we're describing a particle under free, like a free particle, just in a non-inertial frame. Okay, but now we have to understand how to use a non-inertial clock in Newtonian mechanics. So we have to make a transformation where the position variable remains the same, but the time variable changes. And this is something that you typically don't do in Newtonian mechanics, but why not? I mean, it just make a variable change. Of course, you should be able to do it. So we have that the force would be the derivative in time. By using the chain rule, we can break that derivative in time in a derivative with the time hat and the other derivative of time hat. And the same thing we have to do here, because the velocity is going to be a derivative in t, and so we are going to break it up with t hat here and t hat here. And we can set now that m hat is the mass seen by the non-inertial observer is actually m derivative in time with respect of t hat. So it's the change of the rate of clocks. And then we get here a derivative in time hat, mass derivative in time hat of position. This is the velocity. And so this is the force as seen by the non-inertial observer. And now what you see is that you essentially have a variable effective mass during the different clock. If you have the clocks are the same, t and t are the same, this is 1, and the mass seen by the other one is exactly the same. But if the clock changes, it changes in time, you're going to see the mass from the non-inertial observer increase or decrease. And if you are in the inertial observer, nothing is changing. And for the non-inertial observer, things are gonna be harder to accelerate or slower to accelerate, not really because the mass is changing, but because time is changing, and so the rate of change in time is going to be affected. And this is kind of like what happens in special relativity when you have boosted observers, right? Their proper time is different, their clocks are different, and they're gonna perceive an effective mass, an inertial mass that is actually different. So this is all consistent. There is nothing, it looks weird and you wouldn't expect to come in Newtonian mechanics, but this is how the math works. Okay, so we have this, and now we can go and calculate this effective mass. And we have to essentially calculate the derivative of the two time variables, and we know this transformation. It's here, we said it before, and you can do the calculation, and I spare you, and if you want you can pause and look at it by yourself. But what you find is that this factor is exactly this e to the minus b over mt that appears over and over. It's the same thing. And so if you look at the mass, now the mass is going to be multiplied by the inverse. And so the perceived mass, the apparent mass in the non-inertial frame is the mass in the inertial frame times this factor. And this is the same as the variable mass case. And so, if you can go and calculate the apparent forces, of course, what you're going to do is go through the math, and it's going to be very, very similar to what we already did before twice, and you're going to find that MA is equal to minus BV. And so this is the apparent force that the non-inertial observer sees, and it's a force that is dependent on the velocity. So the point here is that the dynamics of the Lagrangian and Hamiltonian for a linear drag are not consistent with a linear drag, but are consistent with a free particle in a non-inertial frame. And this, I think, is really what's going on. Like, you just are in a different frame and things work out to be like this. And so if you're interested only in the kinematics, then fine, you can use this Lagrangian and Hamiltonian to recover the kinematics. But a mechanical system is not just the kinematics, it's the kinematics and the dynamics. So if you are then interested in the dynamic variable, you have to be careful, because these are not going to match the correct physics. You're gonna be likely to make mistakes. And I have seen people make these mistakes, and so be careful. And so now, if we step back, you can see that there is a kind of a subtle and very big problem. Because since different systems may have the same kinematics in different frames, you can't have a frame invariant equation that applies to all systems. It doesn't work. And so, how do the different mechanics solve this problem, solve the problem that you can't just have frame invariant equation that apply to all systems? Well, the way that I see it is that Lagrangian and Hamilton mechanics fix the system. So they basically say, look, we are only going to be interested in the deterministic and reversible forces, in conservative forces, in closed system. We are interested in things that do not change entropy. And then with that, you get the same equation valid in all frames. Now, these equations are frame invariant, and the fact that they're frame invariant is very, very useful. But you're paying a price. You're only considering these forces. And Newtonian mechanics does exactly the opposite. Newtonian mechanics says, look, I'm interested in all forces, but now I have to distinguish which one are really conservative and real and apparent and so on. So they basically say, look, we're going to give you this equation, but this equation is only valid in an inertial frame. And if you change the frame, then you're going to have to calculate your apparent forces and make sure that you know what you're talking about. And this is why these two types of mechanics, right, these two groups, are a little bit different, and you should pay attention and be careful. And this goes back to the more general rant that I promised, is that we in physics are not nearly as precise as we should be when we characterize a system. And it's not a problem of mathematical precision, it's a problem of physical precision. And what do I mean from the difference between mathematically precise and physically precise? Well, suppose that I told you that bunnies eat cats. And you may say, no, that sentence is wrong. It should be bunnies eat cats, because bunnies is plural, and you should use the plural form of the verb. Now, this is what is mathematically correct. You're looking at the form and you're fixing it because there was a mistake. And you can be mathematically precise, but say something that physically does not make sense, because bunnies do not eat cats. Now, you could say cats eats bunnies. And you could say, no, the sentence is incorrect, because it's cats eat bunnies, because cats is plural. But you see, the mistake that I made here, it's a lot less important than the mistake that I made before. And this is why sometimes physicists and mathematicians butt heads, because they're looking at different things. And in physics, we should look first at physical precision, making sure that the things that we're saying are actually accurate at the physical level. And then we can go and look and fix the math and figure out what is the space of functions that we should actually consider physical and so on. But before doing that, we need to be physically precise. And we're not. Oftentimes we're not. We wave our hands, we say, oh yes, the Hamiltonian is not always the energy. What does that mean? Then what is it? If it's not the case, we have to find out. So I don't care whether you agree with all that I said before. Maybe you still think that Hamiltonian is okay for dissipative system. That's fine. What I hope is that you try to be more physically precise, because this is what I care. And this is essentially the subject of my research project called Assumptions of Physics. And all these things that we're doing here are part of this research project. Then we're really trying to be more physically precise, and then after that also mathematically precise. And so if you're interested in this sort of things, you can follow the videos in this channel. You can follow my research on our website, assumptionsoffphysics.org. Or we also have another channel where I actually put the current research. So if you want to have a look at that and contribute, that would be great as well. And thank you for your attention, and see you next time.